Welcome to the second lecture of computational commutative algebra. So in this lecture, we will look at ring homomorphisms. Ideals and some operations on ideals. So let's define a ring homomorphism. So a ring homomorphism is a function between two rings. So let R and S be rings. Sorry, before I forget. From now onwards, when we say ring, this means commutative ring as we defined last time. We might have to deal with some non-commutative rings later, but if that is the case, I would explicitly mention that we are discussing a non-commutative ring. Otherwise, for most of the course, we will only be discussing commutative ring, and therefore we will just call it a ring. So this is as we defined it last time. So let R and S be rings, and so a function f from R to S is a ring homomorphism if it satisfies the following properties. 1. F respects addition. F respects multiplication. And these two should be true for every pair of elements R and R prime inside R. And 3, F takes the multiplicative identity of the ring R to the multiplicative identity of the ring S. So this is what we say is a ring homomorphism. So remember, the first part is that it respects addition, second part is that it respects multiplication, and third is that it takes the additive identity to the additive identity. It takes the multiplicative identity to the multiplicative identity. Okay? Multiplicative identity. Okay? And here I did put the subscripts to make sure that here we are referring to the 1 of the ring R and here we are referring to the 1 of the ring S. Another definition. Let F from R to S be a ring homomorphism. F is said to be an isomorphism F is a ring isomorphism if there exists a ring homomorphism G from S to R, that is in the opposite direction, such that the two composites, so let's look at, so this is the notation for the map in which F is applied first and then G is applied. So this is going to be a map from R to R is the identity map on R. And this is a map from S to S, and this is the identity map on S. The function on R to R given by this composite is the identity map, and this is the identity map on S. Say that two rings R and S are isomorphic if there exists a ring isomorphism between them. So this is one does not have to specify in which direction the isomorphism is, because if there is an isomorphism in one direction, the other map is also an isomorphism. So just one piece of terminology. Okay. We might often say ring map to mean a ring homomorphism. So I want to discuss a few exercises which I will anyway write up in the during the course of these weekly ones or twice a week, but let me just at least discuss them. In part because I might use them later without proofs, assuming that you will do these exercises regularly. So in these exercises, R and S will denote rings, commutative rings, and F from R to S is a ring map. In other words, it's a ring homomorphism. A, F of 0R is the 0 of S. So this was not part of the definition explicitly, but it follows from the definition that this is true. Okay, so one must prove this, which is why this was not explicitly stated. The only part that was stated was about the multiplicative identity. And F of minus R is minus of F of R. Minus denotes additive inverse in the two different rings for all R and R. So in fact, putting these together, we see that if you think of it not as a map of rings, but from the abelian group R plus to the abelian group S plus is a group homomorphism. So it's odd. That's the first observation that we would like to make. And the second thing that F is an isomorphism if and only if F is bijective. So the point of this exercise is, if F is an isomorphism, then there is a G with composites are the two respective identities, so that will automatically make it a bijective function. But so the content is in the other direction, that if F is a bijective function, then the inverse function is a ring homomorphism, and then it has the desired properties. So please check that. Third exercise, there exists a unique ring map from the set of integers to any ring. Given any R, ring R, there is a unique map from the ring of integers. So this is a unique property of the ring of integers when we are studying rings. Okay, so one one more, so it needs a little definition. An element A in R is invertible. So I'm defining invertible, or sometimes it's called a unit. If it has a multiplicative inverse. Recall that in the definition of a ring, we did not say that under multiplication the non-zero elements form a group. Only some elements may have inverses. For example, in Z, only 1 and -1 have multiplicative inverses. Show that f of A is invertible for all invertible A in R. So just to get familiar with these properties of rings and homomorphisms. Now let's look at some examples of these things. Polynomial rings. So then there is a map from R to R adjoint x1 through xn. R is a commutative ring in which ring element R goes to the constant polynomial R x1 to the 0, x2 to the 0 through xn to the 0. So this is a ring homomorphism. So now this ring homomorphism has a certain universal property. And what is that? Let F from R to S be a ring map and S1 through Sn some elements in S. Then there exists a unique ring homomorphism F tilde from the polynomial ring in n variables, n being the number of elements of S that we chose here, 2S, such that F tilde of R is F of R, the given map, and F tilde of Xi is Si for all I. Okay, so what does it say? It says that given any ring map from R to S and some elements S1 through Sn inside S, the ring map extends to a unique ring map from the polynomial ring in n variables over R to S, in which the constant polynomials, the constants get mapped as they were mapped under F, and the variables get mapped to the corresponding elements. So again, this is not so proof. So you have to show that there exists a map. So you can just try to so check, do the details as exercise. I will just define what, I'll just give you a hint. So if there is a unique map and if you can produce it, it would help us to show what it is, I mean to prove its uniqueness. So define F tilde of a polynomial x1 through xn to be, you first apply f to the constants of P, and then you apply that to S1 through Sn. So by this, we mean apply f to the constants, to the coefficients. Okay. So this is the hint, and please try to fill in the details and finish this exercise. Okay. So now let's look at some little bit of Macaulay 2 code to see how this is done in Macaulay 2. So here is how this is done in Macaulay. So I'm defining a ring with two variables x and y with rational coefficients as R. Another ring T with variable T, rational coefficients, call that ring S. Then we define a map, F map. Notice the order in which it's written. So typically when we write arrows to the right, but in Macaulay the arrow is written to the left. And so it's a ring map from R to S in this, from right to left. So it's written S comma R. And then we give a list of elements here. So things that are enclosed in these curly brackets. Okay, list of elements in here which are what these variables should take. So this one says that x will go to t square and y will go to t cube. Okay, and then it's understood that rationals will get map identically to the rationals here. So okay, let's see if Macaulay has understood what we asked for it to do. So here is the screenshot of the output we are checking. So then we are asking Macaulay what is f of x. Then it replies t square element of s. Here we ask f of y. In line 5 we ask f of y. It replies t cube and an element of s. Then we ask f of x squared. It says 2 to the 4 element of s. Definition. Let f from R to S be a ring map. The kernel of f is the set another definition. Let I inside R be a subset. Say that I is an ideal of R if two conditions. A, I is a subgroup of the additive group and B for all R in R and for all A in I, RA is inside I. So it's closed under multiplication by arbitrary elements of the ring and is in a subgroup of the additive group of R. Such a thing is called an ideal of R. Okay. So here is a proposition which you should prove. Let f from R to S be a ring map. Then kernel of F is an ideal of R. So now we would like to see how Macaulay 2 computes these things. So before that, we need to make sense, define just one term, definition. Subset G inside I is a generating set. I is an ideal here, sorry. I is an ideal, G is just a subset. Generating set of I if for all A inside I there exists a finite inside G and corresponding number of elements here, m elements here and m elements here from the ring, such that A is the R linear combination of these m elements. So such a set is called a generating set. The set itself could be not finite, that we have not mentioned anyway. However, for every A, we have a finite subset with this property. A generating set is said to be minimal if no proper subset of it generates I. So it's minimal under containment, inclusion of sets. So just one notation. We will use it mostly for finite sets, so I'll just do it for finite sets. Let's say G is a finite set consisting of n elements inside R. Okay. Then we write with ordinary brackets this is the notation for the ideal generated by G. Okay, so now let's look at an example. So we ask for the kernel of F. Remember, F is this map which goes from rationals x comma y, adjoint x comma y to rational adjoint t. X goes to t square, y goes to t cube. And we ask for its kernel. And it says kernel of F is the ideal generated by x cube minus y square. In other words, every multiple of this polynomial by an arbitrary element of R. So now we can, so we don't know how this is computed. As we progress in this course, we will learn how this is computed, how Macaulay 2 will compute this. But right now, we will use this as a help for us to prove it, that this is the kernel. So the details I will leave as an exercise. I'll list out the steps, but let me just briefly say how it is done. So the map is from rationals adjoint xy to rationals adjoint t, x goes to t square, y goes to t cube. Okay. And Macaulay 2 tells us kernel of f is the ideal generated by y square minus x cube. And we ask, can we prove the statement? Okay. So how do we do this? So first of all, we know that, so now try to prove this by hand. We know that f of y square minus x cube is t cube square minus t square cube. This is 0. So y square minus x cube is 0. Okay. Let p of xy, so now we want to show that the ideal, let me backtrack for a minute. Hence, the ideal generated by y square minus x cube is in the kernel of f. Okay, so we want to prove the other inclusion. So to show the other inclusion, which is kernel of f is inside y square minus x cube. Okay. So take an arbitrary element here. It's a polynomial in 2 variables. Okay. So now the point is, if you take a polynomial in 2 variables, one can think of it as a polynomial in the variable y, where the coefficients themselves are polynomials in x. One can write this using division algorithm as a polynomial times y square minus x cube. All that we have used here is that this is a monic polynomial in the variable y, plus some remainder polynomial xy, where this has a certain property. Either this is 0 or its y degree should be less than the y degree of this thing, y square minus x cube, okay, which is 2. Okay. Because if it had a term that involved y square, one could divide by again and then move it to the side. Okay. So in other words, r of xy is of the form r0 of x, which is the constant part from the perspective of y, times r1x times y. Okay. And one has to show that, okay. So the point is that p is in the kernel, this is in the kernel, this is in the kernel, this is in the kernel. Okay. So both p and this term are in the kernel. So the term on the left and the first term on the right are in the kernel. So hence f applied to r0x plus r1x times y is 0. Okay. And this will, so what does that say? This says r0 of t square plus r1 of t square times t cube is 0. Okay. Now I'll just say what this is. So this is a polynomial in t in which every term has even degree. This whole thing while this is odd degree, the entire thing after multiplying by t cube is odd degree in t, and the way they can be 0, the sum can be 0 only if both of them are 0, and that says that which says that p of xy is in the kernel of Z. Okay. So there are some exercises. One, if you have not seen a proof of the division algorithm for rings like this, then please, for monic polynomials, please learn that and then check these details. Okay, so this is the proof of. So this is how we use these computational algebra systems many times, which is it shows us a computation and tells us what we can prove and perhaps even how we should go about proving it. So in the next lecture, so this is the end of the second lecture. In the next lecture, we will look at prime ideals, maximal ideals, operations on ideals, and then we'll prove what is Noetherian rings, and we will prove, so in the next few lectures, we will prove what is called the Hilbert basis theorem, simultaneously developing some ideas of computation.